So.
And I'm gonna turn down the light
Okay,
just a little. Does that work for everybody?
okay. Well, good morning, ladies and gentlemen.
Let me do your introduction.
It's a real it's a real privilege to be with you today. My name is Jack Hansen, and I'm a participant in the Onyx program at Furman University in Greenville. And we live on the north end of the Furman campus, and I think I've met some of you before. I think since you reopened after the pandemic, I think I did one class here and then a couple, in the it would have been in the 2015, 2019 range. So it's a real privilege to be back with you today. And especially, it's a privilege to be with you to talk about the relatively young and very exciting field of artificial intelligence. So Amanda told me what to do if this happens. So this is an outline of our time together today. First, we're going to seek to define what artificial intelligence is. Then so much is written about the areas of promise and peril associated with artificial intelligence. We're going to just talk a little bit about that. Then we're going to spend most of our time talking about the history of the development of the field, including the key approaches that have been taken, the objectives that have been pursued, some of the key successes that have been realized along the way, and some of the current uses to which artificial intelligence is being put. Then we'll conclude by identifying 3 high-level science and technology challenges that have to be confronted for artificial intelligence to continue to develop in a positive way. Now, let me say that I am not an artificial intelligence or computer science expert by any means. I've had the privilege of supervising groups that do research in that work. But all that is to say that in an hour and a half, we cannot give a complete explanation of artificial intelligence. So our goal together today is to be correct, but by no means complete. Okay? And my hope is that you go away from today with some the understanding of some terminology that is routinely used in articles in the popular press about artificial intelligence, and that this will enable you to read that literature with greater understanding of kind of where it fits. Well,
Amanda should be able to do all the things we need to do yet.
okay. That's not the problem. It's in order to define artificial intelligence, we have to define intelligence. And it turns out that's no small proposition. But I would suggest that for today, we talk about intelligence as having the following component parts. First, there has to be the ability to perceive both the outside world and our own behavior. You and I do that through our 5 senses. A robotic device does that through an array of sensors on board. Then there has to be the ability to write that sensory data to some kind of knowledge storage capability so that it's remembered. And that knowledge storage capability may include not only sensory data, but also information or knowledge that's been picked up from experts in relevant fields. For a robotic device may also include a mathematical model of the way the device itself operates, its parameters and so forth. Then there has to be the ability to use that knowledge to reason about the solution to a problem, or reason about how to obtain a particular objective. And reasoning, those of you who have a philosophy background know that reasoning can be either inductive or deductive, and usually you and I engage in some ill-defined mix of those two. Deductive reasoning involves starting with a set of propositions and working toward an answer. Inductive reasoning depends more on learning the nature of the problem from data that's being gathered. Then there has to be finally the ability to utilize that reasoning to work toward the solution of a problem or a course of action to achieve a particular objective. In computer science terms, that capability is called planning and scheduling. We say that intelligence is artificial if all of the items that are in bold and underlined are done by computer. In a very simplistic way, that's the heart of artificial intelligence. Now let's try this once again. You know, oftentimes when we're talking about what a field is, it's helpful to say what it's not. Artificial intelligence is not the same as automation. What's the difference? Well, I pictured two cars here. The car on your left is the same model car that my wife and I drove from Greenville yesterday. It's a Subaru Impreza. The car on the right is a much more expensive current year Tesla. So our Impreza for driver assist capabilities uses automation. The Tesla uses artificial intelligence. Let me tell you what the difference is. Our Impreza has a set of forward-looking sensors. They look out through the windshield and they sense the distance between our car and the vehicle in front of us. That the data on that distance is continuously written to a computer on our Impreza. And that when that computer, the computations of that computer indicate that we're approaching the car in front of us at a little too high rate of speed, it gives an audio warning. That rate of speed is preset at the factory. When it senses that we're approaching the car in front of us at a dangerously high rate of speed, it actually puts the brakes on for us momentarily to allow us to regain control of the driving situation. That rate is also preset at the factory. There's no reasoning here. It's all about presets. That's automation. Contrast that with the manner in which the driver assist and self-driving capability of the Tesla operates. As we'll see later, a Tesla is a rich array of onboard sensors. And the data from all of those sensors is continuously written to an onboard computer. And that computer is using all of that input to reason about the very best next driving action, to either recommend to you or to take on its own. That is artificial intelligence. It involves reasoning, not factory presets. So that's in a crude way, the difference between automation on the one hand and artificial intelligence on the other. Well, you have probably written or read articles ad nauseum about artificial intelligence and its promise and perils. So just a couple of areas of promise that we will be touching on today are its uses in the medical domain. And what the picture on the upper left here shows is a radiologist looking at a high resolution medical imaging and using artificial intelligence to do more extensive diagnostics and prognostics than would otherwise be possible. And we'll talk about that example in detail. Another area that artificial intelligence is showing real promise is in transportation safety, both highway safety and air traffic safety. And we'll talk about both of those examples more as we go along today. What about Peril? You know, you may have read articles that have kind of an alarmist characteristic about artificial intelligence. You know, it's an existential risk, meaning it's a risk to the existence of humanity, like a nuclear holocaust or something. So when people write like that, what they're talking about is not an artificial intelligence as it exists today, but an imagined generalization called artificial general intelligence. So what's artificial general intelligence? It is the capability of an AI or artificial intelligence system to perform cognitive tasks beyond what it was designed for or what it was trained for. In other words, to take on a mind of its own, to get out of control. That's artificial general intelligence. And there's real debate in the AI community today about, first, whether artificial and general intelligence will ever be realized. And B, if so, we have even precursors of it that might exist today. So the whole thing about artificial general intelligence is still kind of speculative. But there are areas of, of peril or risk that are very real. And let me just mention two. I mean, to me, the most alarming is artificial intelligence enabled deep fakes. You know, deep fake is deceptive imagery or text or voice that is used in a nefarious way, like to manipulate public opinion or action around elections. You remember the day before the New Hampshire primary, there was a robocall purporting to be President Biden, saying basically, don't vote. Well, that was a deep fake. We still don't know who was behind that, but it was taking snippets of President Biden's voice at certain times, stitching them together using an artificial intelligence algorithm to make it communicate a message that he never communicated. This has been done with video imagery, and there are many examples of this. So, I mean, to me, this is the most serious current risk. But there are other kinds of risk. For example, you know, at the dawn of the industrial era, this would have been like the early 1900s, certain types of job categories were eliminated because of the increased use of machinery. At the dawn of the computer era, which you could think of maybe as the 1970s or so in terms of widespread use in the business community, certain other kinds of job categories were eliminated because of the capability of computers. So also in the dawn of the artificial intelligence era, there will be certain job categories that will be eliminated and replaced by AI algorithms running on computers, and that has to be addressed. So there's not a speculation about this. I mean, that's real in the same way it has been in these previous eras. Well, you know, I'd also just like to mention to you a few realities that you don't read about very often in the press, but they're important. I mean, the first is, and I hope you'll come away with an appreciation for this today. In the history of artificial intelligence, there have been important, real, tangible successes that have been realized. Secondly, it's important to recognize that our very best universities are taking important initiatives on their own to push forward the area of artificial intelligence and related fields. For example, MIT in 2020 received a $350 million gift for the establishment of a new college of computing. And the heart of that new college is pushing forward the bleeding edge of research in artificial intelligence first, and second, integrating that AI research with research in other allied fields that may be touched by artificial intelligence. So this is just one example of the really important role being played by academia in our country. And thirdly, major economies around the world have been investing significantly, investing federal dollars in support of the development of this field. And that includes the European Union, China, and the United States. So for example, in 2017, China made a very public announcement about setting aside the equivalent of $7 billion to support its goal of becoming the world leader in artificial intelligence by 2030. The investment strategy of our government has been somewhat different. It has been to provide sustained support for basic research in artificial intelligence. And that support today is at about $3.3 billion annually. And of course, both of these countries, as well as the European Union, have robust private sector investments that are contributing to what's going on in their particular economic sphere of influence. And, we don't know at this point, we can't know what investment strategy and what kind of partnerships and so forth will turn out to lead to dominance in artificial intelligence, if any. But it is important to realize that major economies are investing heavily in artificial intelligence. Well, turns out that this is really quite a young field compared to, say, physics or chemistry or, I don't know, any one of a number of more scientific or mathematical fields that we can talk about. The theoretical foundations of artificial intelligence were laid between the mid-1930s and the early 1950s. Then beginning in the 1960s, there have been successful attempts to simulate or emulate forms of logic or reasoning that we're familiar with because we engage in them. Okay. And we'll talk about several of those. Then, I'm sorry, let's just go. Then beginning in the 1980s, significant work began on an alternate approach to developing artificial intelligence systems. And that involves something called artificial neural networks. And the idea here is this: rather than doing computer simulations, a form of logic or reasoning, the idea here is to utilize a specialized computer architecture called an artificial neural network, which is in some crude sense an analog to the brain, and train this specialized computer architecture by a form of training. So let's just go back a bit. And what this really, I'm sorry, I skipped this, and we'll come back to this at the end. But it's important to realize that in the history of artificial intelligence, there have been two rather different objectives that have been pursued. One is to replace human cognition, where that's relevant. The other is to extend and leverage human cognitive capability, where that's relevant. And we'll see examples of both. And then again, there have been two fundamental approaches. This idea of simulating forms of logic or reasoning that we're familiar with. The other utilizing this special computer architecture called an artificial neural network. And we'll give examples of all of these as we go along. So really the person that is most behind the development of the field of artificial intelligence is Alan Turing. In the mid-1930s, well, I should say Alan Turing was a British citizen. In the mid-1930s, he came to the United States to finish his doctoral degree in mathematics at the University of Chicago. He was brilliant. In 1936, while he was still a graduate student, he wrote a paper that was published and is remarkable for its foresight. In the paper, he put forward two propositions. First proposition, a machine, when you see the word machine in his writing, think computer, a machine can do any computation that a human can do. You already hear in that the seeds of artificial intelligence, right? Replacing human capability to compute with machine capability to compute. The second assertion, that in order for a machine to do such computations, it had to work in binary arithmetic. That is, count in zeros and ones. Not the base 10 arithmetic that you and I are taught to do arithmetic in, 0 through 9 or 1 through 10. You realize that those two statements are the foundations of all modern computing, including your iPhone and so forth. Then in the 1940s, as we'll see in a minute, he was involved in cracking the German Enigma code. Then in 1950, just a few short years before he took his own life, in 1950, he wrote a second seminal paper called Computing Machineries and Intelligence. And in this paper, he posed the following question: can machines think? Or, if you'd like, can machines reason? He did not answer the question, but instead posed a test of a machine's ability to think or reason. Not surprisingly, that test has become known as the Turing test. And you'll see that terminology in a lot of the literature you read in the New York Times or the Washington Post or wherever about artificial intelligence. What is the Turing test? Well, let's suppose in the hallway, on the other side of the wall behind me here, we had a human expert working to solve a complicated problem. And also on the other side of the wall, we had an AI algorithm running on an appropriate computer working to solve the same problem. And suppose we couldn't tell which is which on our side of the wall, but we had two kind of flat panel displays mounted on the wall so we could see the progress of the human expert on one and the progress of the AI algorithm on the other. The AI algorithm is said to have passed the Turing test if its progress in solving the problem is either equivalent to that of the human expert or exceeds that of the human expert. This whole idea of equivalence between human capability and artificial intelligence capability is where the title of the 2016 movie on Turing's life, a part of Turing's life, called Imitation Games, comes from. Many of you have probably seen that movie. If you haven't seen it, I think it's still available on Netflix. And it focuses on just a small part of Turing's life, having to do with his leading a team at Bletchley Park to crack the German Enigma code. So when Turing returned to England after completing his PhD at the University of Chicago, his country was already deeply in conflict with Germany. And a part of the German war machine effectiveness during much of World War II was its use of a sophisticated method of encoding messages that went from the German high command to battlefield commanders. This encoding methodology was termed the Enigma code. And the Enigma code was considered unbreakable, both by Germany and, for that matter, also by the United States. So in the upper left, we're showing a picture of an Enigma machine. This was basically a typewriter that a person at the German high command used to type out a message using normal typewriter keys. But then every keystroke was encoded before it was sent on to the battlefield commanders. The encoding that was used was determined by the settings. See that kind of cylinder looking thing at the top, it's got 4 wheels on it. The encoding was determined by the setting of those 4 wheels. And if you look at all the permutations and combinations of settings possible in the Enigma machine, it was 10 to the 21st power. That's 10 with 21 zeros after it. That was the reason that the Enigma code was considered unbreakable. And oh, by the way, those settings were changed every 24 hours. So if you were to develop a way to crack the code and have it useful in the battlefield context, you had to crack it maybe in not more than an hour or so. So Turing went to Churchill and proposed that a team be developed under his leadership at Bletchley Park to develop a special purpose computer to crack the Enigma code. Churchill agreed. The team was formed, and the computer that they developed is pictured actually on the lower left. By today's standards, it's incredibly slow, incredibly rudimentary, but it was well designed to solve a particular search and optimization problem that is at the heart of decryption and is also very closely related to the algorithmic structure used in some artificial intelligence. Well, of course, we wouldn't be talking about this had it not succeeded. It succeeded wildly. And the movie explains a little bit about some of the, some of the keys to the ultimate success, and also some of the very real moral challenges that were posed by the success. But this is still considered perhaps the most important mathematical and technological accomplishment of World War II that enabled the Allied forces to prevail over Germany in both the Atlantic theater and the European theater. So this is a really big deal. Well, we're missing something. Let's go forward then from the 1940s to the 1960s and Carnegie Mellon University. The person that we have pictured here is a man who became a very famous economist. His name is Herbert Simon. Herb Simon and Albert Newell were two professors at Carnegie Mellon. And together they decided to form a research team to seek to be the first to reduce a form of human reasoning to computer. And the form of reasoning they chose is called means-end analysis. What's means-end analysis? Well, suppose you're going to run a set of errands after you leave the class today. Probably between the time you walk out this door and you get into the car, you will have almost unconsciously run through the order in which you want to run those errands based on what you know about routing and so forth. And then as you're going through running the errands, you may encounter an unexpected traffic jam or road construction or something. So you kind of have to revisit part of your routing and so forth. That's all means-end analysis. So Simon and Newell and their research team were actually successful in doing this. This was the first form of reasoning that was successfully simulated by computer. This was the 1960s. This was a very important accomplishment in its own right because it encouraged other research teams to think about simulating other forms of logic or reasoning. And for that reason, Simon and Newell were awarded the Turing Award for computer science. You know, there is no Nobel Prize for computer science. There's no Nobel Prize for mathematics, for that matter. So the highest form of recognition of this work, and it's important, was this award that they received called the Turing Award. But, you know, Simon had an ulterior motive in choosing this form of reasoning to try to emulate. He saw its potential for detailed studies of an area of economics called bounded rationality in economic decision. And he and his research team utilized this to really push that domain of economic studies forward. And for that, he was awarded the Nobel Prize in economics. So this was, you know, an important early success in the use of artificial intelligence. You can, you know, if you let your mind wander a little bit about generalizing means-end analysis, you can see how it could form the basis for an algorithm, an artificial intelligence algorithm or approach to play a complicated game like chess, you know, which has multiple routings and outcomes and so forth. And in fact, the idea of developing an AI algorithm that could play chess on a par with the world's best chess players, that had been a dream of the artificial intelligence community from the earliest days, but it was just a dream. So between the 1960s and the 1990s, there were some improvements in AI algorithms to play chess, but much more important than that, between the 1960s and the 1990s, you know, there was a dramatic increase in computational speed. So you could do, I mean, you know, Moore's law is basically computer speed doubles once every 18 months. Well, that had been happening for 30 years. So this dream of AI algorithm playing chess at a level of a world master or grandmaster, it really came into the public view in the mid-1990s. Some of you may remember this. There was a highly publicized match between the then reigning world chess champion, Garry Kasparov, and an artificial intelligence algorithm running on an IBM supercomputer called Deep Blue. This match took place in 1996, and Kasparov prevailed over Deep Blue 4 games to 2. There was a rematch the next year. Of course, Gary Kasparov hadn't changed. And the AI algorithm on the computer hadn't really changed either, but the result was the opposite. Deep Blue prevailed over Kasparov 3.5 games to 2.5 games. Well, how could this be? So what we're showing here in the blue line, or let me just, before I say that, some of you may know this about chess. I didn't know this until I started looking more deeply into the history of artificial intelligence. But every chess player that plays at the master or grandmaster level is ranked using a composite score called the FIDE score. In order to be considered a grandmaster, your FIDE score has to be at least 2,500. So what we're showing on the blue line, in the blue line of the plot on the left, is the FIDE score of the reigning world chess champion for every year between 1980 and 2015, which just happens to be the last year that I was able to find this kind of plot. And of course, as you'd expect, in a 35-year period, human reasoning capability doesn't change much. Maybe there've been a few tricks about playing chess that have been picked up along the way, but there's just been a modest change in the FIDE score of the reigning world chess champion from a little under 2,800 to a little over 2,800. Contrast that with the red line. The red line is the FIDE score of the best AI algorithm of that year running on the most appropriate computer of that year. And in that 35-year period, we went from it being no contest, the human expert wins every time, to in 2015, it being no contest, the AI algorithm wins every time. But look where we were in the mid-1990s. We were basically at parity. And when you have two opponents that are very evenly matched, it's no surprise at all that one year you might get one result, and the next year you might get the opposite result. So I only mention this whole thing about chess because I think in terms of public perception of artificial intelligence, I think this might have been the first time that artificial intelligence came into public consciousness in a big way. Well, let's go from playing chess to controlling unmanned spacecraft involved in deep space exploration. So in the mid-1980s, NASA made a very important strategic decision that turns out to have a lot of relevance to artificial intelligence. The decision was this. The decision was to field a small number of unmanned spacecraft for real deep space missions. But those missions were kind of a secondary purpose. The primary purpose of on each of these spacecraft was to test a small number of sort of bleeding edge technologies, which, if successful in space, had the potential to revolutionize unmanned space exploration. So the first of these missions was termed Deep Space One. And the picture on the left here is an artist's concept of the Deep Space One spacecraft. And as this artist's conception shows, the mission it was assigned was an asteroid flyby mission. So this is relevant to our discussion today because this was the first in-space test of an artificial intelligence algorithm. That artificial intelligence capability was deemed remote agent. And it used a form of reasoning that we'll come to in a minute, explaining in a minute. It's called model-based reasoning. So what was the purpose of remote agent? The purpose of a remote agent was to receive data indicating the health of all onboard subsystems and components. And when that data stream suggested the failure of a component or subsystem, to figure out the best workaround of that failure to allow the spacecraft to continue its mission successfully. That was the essential function of remote agent. Again, we wouldn't be talking about this today had it not been a remarkable success. So a little bit more about remote agent and Deep Space One. The picture here on the left is actually a picture of the Deep Space One spacecraft undergoing final test and calibration. And this is before the protective shroud is put over it, you know, that protects the innards of the spacecraft during launch and during in-space operation. Well, we said that the form of reasoning used was model-based reasoning. What's model-based reasoning? You, like I, may have engaged in model-based reasoning as a young parent. When our daughter was about 2, I went to a local store to buy a kit for an outdoor swing set. It was in about 1,000 pieces. I brought it home, started assembling it, and when I got about 2/3 of the way through, I realized I was missing a few pieces. Well, my first thought was not, how do I get this thing in the car, which I couldn't have at that point, and get it back to the store and complain. My first thought was to ask the question, can I repurpose the pieces I do have in such a way as to end up with a safe, workable swing set for our daughter? That form of reasoning is called model-based reasoning. And the model in that case is the schematic of how the swing set goes together. Let me give you another example of model-based reasoning. Anyone who uses a recipe to cook probably has engaged in model-based reasoning. You may have had the experience that you start out following a recipe, you get partway through, and you realize you don't have as much of a particular ingredient as is called for in the recipe, or maybe you don't have it at all. Hopefully your first thought is not, I'm going to throw this out and give up. Probably your first thought is to ask yourself the question, can I change the proportions of the ingredients I do have, or perhaps use another ingredient that's not called for, but what I have immediate access to, and end up with a suitable result? That reasoning you're going through there is model-based reasoning, where the model is the recipe. In the case of remote agent, the model being used was a mathematical model of how the various components and subsystems of the spacecraft were hooked together to control the spacecraft's performance. So when a failure was occurred, the reasoning that was done was the best workaround of that failed component. So how did NASA plan to validate this in space? Well, they had programmed in a failure of a critical subsystem to take place at a known point in time before the asteroid flyby. The day came for the failure to take place. It took place, and remote agent worked flawlessly. They, of course, knew this from the telemetry that was coming back from the spacecraft. A couple days later, a completely unforeseen failure of another subsystem took place. And the result was the same. Remote agent figured out how to use the remaining components and subsystems to allow the mission to continue successfully. This would have been a huge accomplishment had it taken place yesterday, but it took place in 1999. And for this accomplishment is still considered one of the great achievements in the history of artificial intelligence. Well, remember we talked early on about the fact that there have been 2 objectives that have been pursued in artificial intelligence. One is to replace human cognitive capability. The other is to leverage and extend it. The person most responsible for pushing forward that second point of view is pictured here. He's an eminent computer scientist. His name is Ken Ford. Ken is the founder and still the CEO of a research institute called the Institute for Human and Machine Cognition. Ken worked for me for a while I was in NASA. I worked for Ken for a while when, helping him run his research institute, and we've done consulting together as a team for several years. But I make the point that I'd just like to make the point and leave with you the point that whereas, say in a space application, it's obvious that what you want to do is replace human cognition. Or think in the economics example we used before, where you want to try to simulate some broad economic phenomenon or something. What you're seeking to do is replace human capability in that model. But there are a range of applications where what we really want to do is utilize artificial intelligence to enable improved performance by human experts. So one example is air traffic management. Every time you get on a commercial plane, from the time your plane leaves the departure gate, through the ascent, the cruise altitude, descent, to the time you get to the arrival gate, the trajectory of your plane is under the control of several teams of expert air traffic controllers. What does that have to do with artificial intelligence? Well, over the past decade and a half, a set of progressively more sophisticated advisory tools have been fielded at airports like Hartsfield, like Charlotte Douglas, and others that advise air traffic controllers on the course of action that's best for the next period of time. And that will continue to be an important and developing domain where we seek to not replace air traffic controllers, but enable them to do their job more. Another area has to do with human control of robotic spacecraft that are exploring the surface of Mars as our proxies, and we'll come back to that example. A third has to do with appropriate interpretation of very complicated data sets that come from experiments that scientists have developed. So, basically assists in data interpretation. And particularly important in this regard, is the ability for scientists to not see correlation between variables. We're very good at seeing, well, if one variable changes, there's another variable that also changes. That we can see pretty clearly. What we're terrible at is identifying cause-effect relationships. That is extremely difficult. And there have been a set of AI algorithms developed that assist scientists in identifying cause-effect relationships in the data sets that they're working with. But let's talk a little bit more about this, this thing of the relationship between a rover operating on the surface of Mars and the on-Earth science team that actually controls what the rover is doing. Since 1997, we've had several robotic rovers, progressively more sophisticated rovers, exploring the surface of Mars on our behalf. And we can tell the same story about at least the last 3 or 4 of them. Talk about the most recent one, the Mars Perseverance rover. The Mars Perseverance is controlled by an on-Earth science team that is divided into sub-teams by discipline. So there's a sub-team associated with geology, one associated with life science, one associated with atmospheric science, and the list goes on. At the end of each Mars exploration day, all of the data collected by Perseverance that day is downloaded to each sub-team, along with a map that comes from the program office indicating an estimate of the range of travel of the rover for the following day. So on the basis of all that information, each sub-team develops its exploration priorities for the next day for the rover. Now, as you can imagine, different sub-teams have different priorities, because they have different responsibilities, different areas of expertise, and so forth. This is where artificial intelligence comes in. The exploration priorities of each of the sub-teams is loaded into an artificial intelligence-enabled planning and scheduling algorithm. And that algorithm develops the trajectory for the rover for the following day that allows it to achieve the largest number of high-priority science goals. How big a deal is this? Turns out it's huge. The manager of NASA's Mars exploration program and his team have done detailed studies of the impact of the use of this AI planning and scheduling capability on science outcomes. And this is a serious number. They have come to the conclusion that the use of this AI-enabled planning and scheduling algorithm has increased the science output of each of our rovers by a factor of 10. That is huge. You think, you think about the amount of time, the amount of expense, the number of rovers, however you think about it. I mean, this is a huge result. And it's just indicative of the importance of this idea of using artificial intelligence to extend human capability as well as to replace it. I'll just mention that I don't know if any of you would be interested in learning more about one of the very interesting interactions between a robotic rover serving as a proxy and an on-Earth science team. And if anyone's interested, a computer science friend of mine, he's very well known, his name is Bill Clancy. He was embedded for a couple of years with one of these science teams, and he's an expert in ethnography as well. And he's written a wonderful book on this topic. It's called Working on Mars. It's published by MIT Press. If anyone is interested in learning the kind of the nuts and bolts of how this works, well, I would give Bill's book to you. Okay, everything we've talked about so far is artificial intelligence realized by simulating a form of logic or reasoning by computer. Now we're going to switch gears to artificial intelligence that is enabled by a specialized network architecture, computer network architecture. These are termed artificial neural networks, and they were intended by the people who conceived of this idea as being a very crude analog to a brain. So what I've shown in the upper left here is a schematic of a very, very simple artificial neural network. So in this little schematic, each circle represents a simple computer, and each line represents a data pathway. That is a connection by which data can be passed from one computer to another. Now, the whole idea, or the analog that the originators of this concept has, was that each computer is kind of like a neuron in the brain. And each data pathway is kind of like a neural pathway. So, and that's the extent of it. I mean, that's pretty, that's pretty lame on one level, but that was the motivation for developing this kind of network architecture. So, and I'd also mentioned that what we're showing here is a two-dimensional version of a network. We'll talk in a bit about the fact that most real networks are three-dimensional in character, but also that these simple computers are organized in what are called layers. So going left to right, the green layer is called the input layer. That's where data or problem statement goes in. Then there's first hidden layers, the first orange layer, second hidden layer, the orange layer, second orange layer. And then where the output comes is the blue layer. That's called the output layer. So each simple computer has only a couple functions. And let's focus on the topmost orange computer in the first hidden layer. You'll notice that it receives data from every computer in the green layer, the input layer. So one of its functions is to sum those inputs from the computer that it's receiving from the computers in the prior layer. That's one of its functions. Its second function is to multiply the signal it sends on to each computer in the next layer by a number called a weight. And the weight that it uses for the signal sent to each computer in the following layer can be different. But this term of weight is important. So the end game here is, and we'll get to how this is achieved, the end game is if I put in a problem statement on the left-hand side, the network gives me the correct answer to the problem on the right-hand side. That's the end game. So how do we get there? Well, the basic idea of an artificial neural network is that it's trained by a set of by a set of realizations of problems where we know the input and we know the corresponding output in advance. And we'll give 3 examples of this. And I think this will make more sense to you as we continue to look at examples. But the basic idea is this. We set all of the weights in the network to an arbitrary level. Let's say we set all of them to 1. Then we send the problem statement in the left-hand side. It propagates through the network. It gives us an output or set of outputs. And of course, they're wrong. We take the difference between that predicted output and what we know to be the correct output, and it's propagated backwards through the network. And as it's being propagated backwards through the network, utilizing a mathematical formulation called backpropagation, it adjusts the weight at each of the weights in each of the computers such that the next time we put that same input in, it gives us an answer that's closer to correct. And we keep this back and forth going, same input, and then propagating it through and taking the difference between the known output or the predicted output and the correct output, propagating it backward and adjusting it. And we continue that until when we put that input in, it gives us the correct output. That's the form of the training. Now, let me say, from my point of view, I have no idea if this is how a brain works. But this formulation does turn out to work with this computer architecture. Okay, just one more thing, and then we'll talk about examples. I mean, really serious research on artificial neural networks, particularly 2-dimensional artificial neural networks. You know, simple ones like the ones that we pictured here schematically. It began in the 1980s and continued through that decade. In 1990, a research group at the University of Toronto, headed by the man pictured here, his name is Jeffrey Hinton, began experimenting with 3-dimensional generalizations of artificial neural networks. That is, they developed networks that were essentially stacks of these 2-dimensional networks, one on top of the other, where there was interconnection among the various stacks. And they also developed a 3-dimensional generalization of the training algorithm called backpropagation that would work with 3-dimensional networks. That work is the foundation of all modern, what is called deep learning, and all modern generative artificial intelligence. That generalization of the 2-dimensional neural network concept to 3 dimensions. So let's look at some examples. I think for me, examples will really help. So the first example we're going to look at is not very societally significant, but for me, it helps understand, okay? So here is the problem. The problem is, can we use an artificial neural network to correctly estimate the repair cost of a fender bender based only on a photograph of the fender bender as an input? Understand? So we use a digitized version of this photograph as the input to the artificial neural network. And with the weights set arbitrarily at the beginning, that's propagated through the network, and it provides the first estimate of the component parts of the repair cost and the total repair cost. They're wrong. So we take the difference between, and of course, this repair has already been done, so we know the correct answer. So we take the difference between the predicted repair cost and its component parts and the actual and propagate it backwards, and in so doing, adjust the weights. And we do this again and again and again. And after maybe hundreds of iterations, we get to the point where for this photograph, or for this fender bender, the network predicts the correct components of the repair cost and the total repair cost correctly. Then we go to another fender bender. Same network, and we're not starting from scratch. We're starting from the network, the trained network as it exists for this photograph. Then we take another fender bender and we go through the same process. Continuing to refine the training and another and another. And by the time, depending on the problem, by the time we've done this for literally hundreds or maybe thousands of fender benders, we are at the point where when we present a photograph of a fender bender that has not been used in the training of the network, it gives us the correct repair cost. First time. Now, in 2018, about 10 to 15% of all auto body repair cost estimates were done using this methodology. The last number I saw was, I think it was probably like, might have been late 21, 22, I can't remember. But at that point, it was somewhere in the 60 to 65% range. My wife and I have State Farm auto insurance, and we have apps on our iPhone, and part of that app is a camera activation that allows you to take a picture just like this, to upload to State Farm for them to do their own internal estimate of what the repair costs should be. So as I said, I think this is an illustrative example, but it's not a societally significant one. This is more societally significant. There is an eminent computer scientist at MIT who is herself a breast cancer survivor. A few years ago, as she was recovering from the treatment from breast cancer, she began asking herself, is there a way that we might be able to use artificial neural networks to accurately predict the probability of a patient developing breast cancer over some finite period based only on initial mammography? So that was the problem statement. So she and her research group formed a partnership with Mass General Hospital, that's Harvard's teaching hospital. Those of you that are familiar with the Boston area know that Mass General Hospital is located just diagonally across the Charles River from MIT. So what did Mass General Hospital have that was relevant? They had detailed patient records for about 200,000 patients who had received mammography and been followed up for at least 5 years after that initial mammography, in terms of whether or not they had developed breast cancer, and if so, when. They used those 200,000 patient records as the training set. So the input was a digitized form of the mammography. The output was information for that patient of when they had developed breast cancer, and if so, when. And they limited their consideration to a 5-year window beyond the initial test. So then the question came, how were they going to test the utility of this? Mass General Hospital, of course, has research relationships with leading hospitals around the world. So they in turn formed a partnership with, I think it was a total of 7 hospitals, some in Asia, some in Europe, who together had equivalent records for 60,000 patients. And the fact that this was used to test the algorithm was very important in its own right, because the ethnic makeup of the patients among those 7 hospitals is very different than what Mass General Hospital and its affiliates saw in the Boston area. And also different countries, hospitals in different countries, utilize different manufacturers for high resolution imaging capabilities. So there were some differences in the details of how the mammography was done from a detail standpoint. Nevertheless, the initial results were astounding. This capability correctly predicted the likelihood of a patient, an individual patient, developing breast cancer within that 5-year period, correctly in 76% of all cases. That's better than 3 times, that's more than 3 times better than the currently existing methodology. It's huge. So this was the initial result, and work on this is continuing. And also, interestingly enough, as you'd imagine, there's also work going on now in using a similar capability to do predictive diagnosis or prognosis for other forms of cancer, where we also depend on high resolution imaging to understand the details of a particular cancer in a particular patient. So this is huge. Well, let's talk about a third example, and I should say all of these are examples of what is called deep learning, meaning that you train the network to correctly predict an answer or a solution on the basis of the statement of a problem, okay? So the third example I thought it might be interesting for us to look at just briefly is self-driving cars and driver assist. There is an organization in the United States called the Society of Automotive Engineering, or SAE. Some of you may be familiar with it. SAE has done us a tremendous service in helping us understand driver assist and self-driving capabilities by developing this taxonomy, which goes from, like, my Subaru would be a level 1. That's where, you know, in an emergency situation, an onboard system is able to take over one driving function, like braking, momentarily, to allow you to regain control of the driving situation. A modern Tesla would be kind of more like level 3, where the driver is in supervisory control at all time, but under the driver's supervision, the car is capable of driving itself in most circumstances. Level 4 is the domain in which a fleet of driverless taxis is currently operating in downtown San Francisco. And we'll talk more about all of these. So I'm going to talk a little bit about the way in which Tesla's self-driving and driver assist capability work. And I'm only choosing Tesla because of all the companies involved in this, they've been most open. Yeah. So, you know, most of us think of a Tesla as a set of electric motors and batteries on wheels, but you could equally well think of a Tesla as a sophisticated set of sensors on wheels. So depending on the model Tesla you have, some have long distance radar, some have ultrasonic sensors, all have a substantial number of cameras looking in all directions. Each one of those cameras is running a sophisticated image recognition software package. A few Teslas are capable of receiving satellite imagery of surrounding traffic, and all Teslas are recording not only those sensors, the data from those sensors, but also data from all normal driving functions, you know, cornering, braking, accelerating, and so forth. Now, all of that data is fed into the onboard artificial neural network as a basis for that network making the decision of what to recommend to you for the very next driving action, or if it's in self-driving mode, doing it for you. But in addition to that, all of that data is being written to an onboard storage device on your Tesla. Every 24 hours, all of that data is uploaded to a centralized data repository that is retained by Tesla. Tesla estimates that the data it receives daily is equivalent to about 1 million miles of training data for its artificial neural network. So Tesla then uses all of that data, which it's continuing to accumulate, all of that driving data, to continually refine the training of the artificial neural network used for driver assist and self-driving capabilities. When their internal tests show that the weights of that network have changed enough to represent even an incremental improvement in actual performance, Tesla downloads all of those refined weights to your Tesla, like you and I receive downloads to an app on our phone when the app developer has done something that makes it work a little better. So that's how training data is gathered that is used for self-driving and driver assist capabilities. Well, how's it work? I'm going to just give you two out of what are thousands of video segments that you can watch on the web of a Tesla in self-driving mode. I'm just going to show you two very brief ones, and then we'll talk about the taxi fleet. So in the first one, the car is driving on a remote back road where the speed limit is 25 miles an hour. And you'll see that as the car is coming up a hill, you'll see it come on a pair of joggers in the right-hand shoulder. The onboard self-driving capability correctly perceives that it cannot see over the hill and therefore know whether it's safe to pull out and go around the joggers. So it slows to the speed of the joggers until it gets high enough on the hill to see whether or not there's oncoming traffic. So here it's coming on the joggers. You see it slows to the speed of the joggers till it gets high enough that it can see over the hill. Okay, so that's a slow speed example. This is a very different driving example. This is in suburban Los Angeles. It's nighttime driving. The speed limit is 45 miles an hour on a road that's 8 lanes, 4 lanes each direction. And in this case, the Tesla is going at about 25 miles an hour because of heavy traffic. And it correctly perceives that it's in the second to the rightmost lane. It correctly perceives that there's no barrier to it going into the right-hand lane and perhaps being able to go a little bit closer to the 45-mile speed limit. But the minute it does that, it sees a stopped emergency vehicle in the rightmost lane. So it quickly reverts back to the original lane. You're just starting in the right lane. Here it perceives the stopped emergency vehicle and quickly goes back to the left lane. Now, these are the sort of things you'd hope you'd see, but they're anecdotal. The only, more systematic test that I'm aware of self-driving capabilities is associated with a fleet of driverless cabs that has now been operated for a little over a year in downtown San Francisco. These don't use Tesla's self-driving capability. They use that of a company called Waymo, which was bought by Google in the last year or so. So you can think of this fleet of self-driving cabs as being a partnership between Waymo and Google. Once again, this fleet operates in a well-mapped part of downtown San Francisco. What we're showing in the picture here is the driverless Waymo cab taking a left turn from one street onto another in downtown San Francisco. So the question is, after a year's operation and roughly a cumulative of 1 million miles of driving, what's the safety record? Well, I just extracted a few key points from that here. First, over that year, another vehicle ran into a Waymo self-driving vehicle 28 times. A Waymo vehicle ran into another vehicle 4 times, and in 2 of those 4, it was clear that it happened because the other vehicle cut the Waymo vehicle off. And finally, during the year, a Waymo was involved in 4 what are called serious incidents, and that they could have, though didn't, result in some form of bodily injury. None of those were judged to be the Waymo vehicle's fault. So the question is, how does that safety record compare to the record that would have been logged if all of this fleet were operated by professional taxi drivers? The answer is, it's just about equivalent. So this is very encouraging about thinking where we are and where we might go in terms of the continued development of self-driving capabilities. I had an interview the other day, someone said, I think rightly so. They said, in order for self-driving capabilities to be widely adapted, it will not be enough that they're as good as professional human drivers. It has to be much better. But I would just submit to you that it looks to me like that's the trajectory that we're on today. We're not there by any means, but I think we're on our way. Well, the final topic we'll say just a bit about is generative artificial intelligence. And this is the real buzz in the artificial intelligence community today, caused largely by a program that some of you may use called ChatGPT. So what is generative artificial intelligence and how is it different from deep learning? Both use very sophisticated artificial neural networks. The two distinctions are the purpose and the form of training. So the purpose of generative artificial intelligence, whether it's for verbal use, artistic use, a whole range of uses, the purpose is to generate content on the basis of a set of commands or queries that you give it. So let's take ChatGPT as an example. This is an example that's used by OpenAI, which is the parent company of ChatGPT. The query is, write a story on a moon landing that's appropriate for a 6-year-old. That's the query. The result is a 2 or 3 paragraph story on a moon landing that's age appropriate. So I'm sure you have used this for much more sophisticated purposes than that, but that gives you a sense about the generative nature. It's writing a new story, okay? So, and this has been used in a whole array of domains other than writing, including computer programming, language translation, artistic development of artistic expression, and very recently, and we'll talk more about this, medical diagnosis. So one difference is the objective. Deep learning is problem solution oriented. Generative AI, as the name suggests, it's creation of new expression or something. The other important difference is the manner in which the artificial neural network is trained. So we've talked about how training for deep learning has taken place in the 3 examples we talked about, the auto body example, the breast cancer example, the self-driving example. Well, let's take ChatGPT specifically. Before there is any training of the supervised nature that we've talked about for deep learning, or training where you know a problem statement and you know a solution. Before that, the neural network for ChatGPT undergoes a form of unsupervised training, which is essentially the equivalent of uploading to it literally thousands of books or hundreds of millions of words that allows the network in an unsupervised way to form an underlying understanding of the structure of the language. So that's done first. Then the supervised training is done. And we could go on about this all day and we'd be way beyond anything I understand about generative AI. But there is that essential difference in the training. Well, so in the 1970s, there was a really serious effort in the computer science department at Stanford University to develop an AI algorithm that could successfully diagnose infectious diseases based on a physician's observations of the presenting symptoms of a patient. This used a form of reasoning that we haven't talked about, but it's another example of what has been done in the history of artificial intelligence. So expert systems, the idea is that in this case, you elicit the knowledge of the world's foremost experts in infectious diseases. You reduce that collective knowledge to a set of if-then statements, if the patient has such and such a lesion, and if the patient has such and such a temperature and some other symptoms, then the probability that they have infectious disease X, Y, Z is so much. And that it turns out that work at Stanford was very successful. It was demonstrated at Stanford Hospital that a primary care physician could use this and diagnose infectious diseases correctly at the same rate as the world's foremost expert in infectious diseases. But it was never widely implemented. Why? Well, it turns out that it is incredibly expensive and time-consuming to do this form of knowledge elicitation with people who are at the top of their game. Like the best infectious disease experts from around the world. So I just determined that the cost benefit wasn't there. Well, let's fast forward to generative artificial intelligence. The paper on this appeared January 11th of this year. It has not yet been peer reviewed, but this is work done by a very reputable computer science research team. And what they have done is they have taken recordings of patient interviews that have been done by primary care physicians. You know, both voice recordings and notes, both. And they have used that from literally many thousands of interviews to train a generative artificial intelligence network. And train it specifically to do the primary care, the sort of interview that you and I get from our primary care physician if we go in and say, I'm not feeling good. So the physician begins to ask you a set of questions, and the follow-on questions are determined by what you say at each stage and so forth. But we routinely go through this. So the idea here is to replace the primary care physician in the process of that intake interview. So they train the artificial neural network. Then they've done extensive tests of the performance of this network in comparison to a large population of primary care physicians. And it's iPod. So on the left, the blue line is the percentage of primary care physicians that get the diagnosis correct first time, after 2 tries, and so forth. So let's focus after 2 tries. After 2 tries, primary care physician will have gotten the diagnosis correct about 73% of the time. The orange line is the corresponding result for the generative AI system. The second time, it is right 85% of the time. And you see, there is no place where the primary care physician performance exceeds that of the generative AI system. I think this is the future of medicine in a very real sense. And the idea here, again, is not to replace primary care physicians. It is to recognize that this initial intake interview is time consuming in its own right. And allowing it to be done where you or I interact with the system using normal conversation, it with us, we with it. I mean, we're not using a keyboard or anything like that. And then those results go to the primary care physician so they can do the more difficult things and do them better. So again, I think this may well look like the future, at least a part of primary care. Can we just wait until the end so that? So we're almost done. I just mentioned that there are 3 areas, high-level challenge for artificial intelligence. One has to do with generative artificial intelligence. That is to, and this is well publicized, we really need to work on developing a set of guardrails in each generative AI program to assure that what they produce is safe, legal, and that is really hard. The second is to develop improved ways to combine the best of human expertise and artificial intelligence to allow continued improvement in the performance of really complicated tasks like air traffic management. And there's a third one. You may have noticed that we talked about successes that have been realized using simulations of various forms of logic. And we talked about successes involved in using artificial neural networks. We never talked about any synergistic use of those 2 different approaches because we don't know how to do it. So there's a third, potentially very rich area of research. So let me just go back to what we said early on. There are essentially 2 objectives that have been pursued in the history of artificial intelligence. One is to replace human cognition. The other is to extend it. There have been 2 essential approaches that have been taken to developing artificial intelligence capability. One is to simulate or emulate forms of logic that you and I are familiar with because we engage in them. The other is to use a specialized computer architecture called an artificial neural network that at some rudimentary level is an analog to a brain. And finally, as you know well, much of the current buzz around artificial intelligence has to do particularly with generative. Although work across this spectrum it continues, we just don't read about much of it except in popular literature. Well, let's stop there. And you had a question.
And one question, you mentioned that the medical diagnostic example you gave might not be cost effective. Is that because it's just so hugely expensive to generate the AI version of the nerve?
No, the time of the world's experts in a field is so expensive.
Okay,
It's the knowledge elicitation from the experts that is has overwhelming
so
cost.
who's selecting the experts and who would be coordinating that? And is that
Well,
even?
in this
is that
particular
even-
case, Stanford Hospital did. Stanford's an internationally known hospital. They knew where to go for the world's experts in infectious diseases.
So
So they
that's like a research project. But once this
Oh.
results has been
Mhm.
published, then it looks like you could generate that kind of chart much more cost effectively without going to the greatest expert, but just the run-of-the-mill experts.
Yeah, see, but that wasn't what they were really after.
Right.
What they were really after was enabling your family doctor or my family doctor to have diagnostic capabilities on the same level we would receive if our family doctor referred us to the best hospital in the United States for that specialty. That was what they were really after. Yes, sir.
Jack, early on, you mentioned AGI, artificial general
Right,
intelligence, and I can't remember if you said it, but some pundits say never gonna happen, and you can find another variety of pundits and say 3, maybe 4 years. Here's the question.
Right.
How would we know, and specifically, how would you know, how would I know that we got there?
Well, I mean, I think that's a very good question, and I don't know. I mean, I think, a lot of things we don't really know until it's in the rearview mirror. And so, we might not know that a particular capability has emerged that in fact gains a mind of its own. In other words, acts outside of the range that we have specified it act in, or for purposes that we didn't specify. But I wonder about that too. I mean, that's a great question.
Jack, I've got a question in the Zoom room
Okay.
from Suzanne. She says, can data in a repository be tampered with?
Yeah, I guess I don't really know the answer to that question. I mean, we certainly know that databases can be tampered with when they have certain kinds of structure and information. But so that's one kind of example. I think it's a little bit different, like when you're collecting driving data. It's not as clear to me that you could get in and substitute what would pass any initial filter for legitimate driver data because of the way in which in the case we were talking about, the way in which Tesla encodes its data and stores its data in its centralized repository. But that's a great question. I mean, never say never, at one time when I worked for the Department of the Navy, I had a very high security clearance. That was a long time ago. A few years ago, I got an email saying the database that contains the information from interviews of other people that were done about you has been compromised. So we're giving you identity theft protection for 3 years. Okay, so I mean, it's one of these, it's really hard to say, I think. Yeah.
Okay, let somebody else go. Somebody else have a question? If not, I'll go again.
Okay.
I don't hog all the time. Okay, so the first question was too hard. Let me ask an easy one.
Sure.
On a day-to-day basis, do you use chatbots for any practical purpose?
No,
Hmm,
but I have friends that do.
Okay,
So I don't know what, what kind of course offerings and related to artificial intelligence you've had this year at the program here. At the University of Georgia, but at the Ollie program at Furman. We had an 8-session introductory course in artificial intelligence in the fall. We had a second 8-session introductory course that's going on right now for the winter term. And also, of course, my wife is taking on the use of generative artificial intelligence tools. And then in the spring, a philosophy professor friend of mine and I are doing a 1-session thing on the philosophical and ethical issues that are raised by artificial intelligence and its application. And there are a range of such issues, starting with the manner in which cracking the Enigma code was used by England and extending to today.
shameless self-promotion, that's exactly what the class I'm teaching.
Good.
Tell us when, Jack.
Very nice,
Okay.
That's great.
and there are a few seats left, but still fine.
Is there gonna be
Yes.
a standing?
Most of the examples you gave here are all US based. How are other countries such as China doing? Do they have the same concerns about guardrails and all of that?
So I think the honest answer is that US, particularly US researchers and also companies that are in the startup mode in the US tend to be much more open than their counterparts in China. And that, that's largely government policy driven. So I think it's really hard for us to know the answer to that, if we definitively.
Yeah.
I mean, I wouldn't feel comfortable in taking 2 or 3 anecdotal examples and making generalizations about what's going on in China, whereas in the US, we can see in the open literature, we can see enough of what's going on to draw some real conclusions. And that's not just for artificial intelligence. I mean, there's a lot of debate right now, for example, about who really is more advanced in the emerging area of quantum computing. And, there's one research group in particular that in China that has done some really amazing things. There's a Google group that's done some really amazing things. But in the Chinese case, it's hard to know if that's the only group that's really working or if it's the most advanced. I mean, we just don't know. I mean, in the United States, by charter, anything that the National Science Foundation funds, anything that NASA funds, and particularly those two, is open to the public. And so we have a much different picture in terms of fullness than we would, not for the European Union, but for China. Yes, ma'am.
The Genome Project, opening that up. And
Oh, yeah.
what that provides. Is anybody in here in healthcare? I have a 40-year background in it, as does my husband, and he's a neuroradiologist. I'm a nurse practitioner, and I am thrilled about the direction this is going. And you talk about, why isn't it cost effective to have the world's minds made available to the primary care's laptop? But when I think about the area where healthcare probably dropped the ball the most significantly over the 50 years of my career, it's mental health. And this opportunity, not that you're not talking to, someone who has a lovely voice, but is Alexa.
Right.
The idea of being able to reach out to virtually all of us
Right.
at different times and speak to a voice that can usher us forward or to a location is very exciting.
It's huge. And also that, to think about populating that in some way that's not compromising, populating that with the equivalent of intake interviews that are done by primary care physicians, but in the mental health domain. I mean, that would be enormous. Yeah, so that's a great observation. Well, I think our time is up. It is up. And thank you all for your attention. It's great. being with you.
Appreciate the use of some very well selected examples.
Oh.
I appreciate that.
Well, thank you. I mean, there are, of course, there are many more examples and many things that could be.
Thank you, Jack.
Thank you.
Check out.